So good morning, everybody. My name's Ken Grob. I'm with Elma Electronic Inc. And I'm waiting for this to start. So today, we really have a relatively straightforward presentation. There's like 4 big trends we want to take a look at. So the title might be a bit confusing, Solving the Unsolvable, how technology acceleration is transforming information processing and enabling new capabilities. And the thing on the right is kind of looks like a nifty light that you hang from your hallway, but actually it has to do something with quantum computing, and I'd like to get to that in a little bit, but talk a little bit about our journey that we've taken this year, much like we talked about last year, of what's been happening in our industry and what we've been able to sort of touch and skip over the waves and address. So in solving the unsolvable, if we look at this as we go through the presentation, it's going to be a progression. And over the past 2 days, we've had quite a bit of discussion about edge computing. So one of the trends that we wanted to take a look at was the rapid increase of compute performance from edge to network to cloud. Another point is acceleration of technology, how it's accelerating. This is almost blinding when you look at what we've been seeing for technology increase as the years go by. So acceleration of new technology like generative or predictive AI that can be distributed throughout the end-to-end compute chain. Another point would be new security paradigms required to ensure data security up and down, driving the need to plan and implement specific use case security considerations end to end, thinking about from maybe the edge on the left, going through the network, and then up to the cloud on the right. And the last point is something new, maybe the 10,000-pound gorilla in the room, quantum computing. Interesting thing about quantum computing in the last couple of months is that there's been some assertions made that this may be actually on the horizon in a way that it could be useful to more than just researchers, but actually become a technology that we could embrace, and it could be potentially disruptive. So we look at, as we've been talking about for the last couple of days, the edge premise, or modern edge computing. And I put a term up here called classic. What we realized while we were kind of kicking this thing around again was that the model for edge is kind of common to the commercial applications, the industrial applications, and also the mill or the rugged applications or the mil-aero or the public sector. So you've got some basics that are the same. So if you look at the far left, the first thing we're looking at is local embedded computing of sensor processing and control, and sort of the applications running from top to bottom of what they may be. Then to the right of that, what we're looking at that edge box is a box that could be an intelligent gateway doing something called MAC, multi-access edge computing. And it faces to the left the applications and the services that it provides to the applications. And to the right, what it's doing, I think, is giving you a look at different potential connectivity that you'd have between the left side of this block and the right side of the block that gets you serviced by a network layer in the middle to provide network connectivity. So then, if we take another look and we move to the right, beyond the network block, what we're looking at is network services. And in here, this list may change depending on whether you're looking at it from a mil-aero point of view or you're looking at it from a commercial point of view. But if we look at the cloud, you've got Microsoft Azure, Amazon Web Services, Google Cloud, the list goes on. And these are services that are available today, obviously, and people are leveraging these services to do what they need to do. And some don't do any edge computing at all. They just use these services as compute services that are really enabling, and people are using these every day. To the right of that, you've got what's associated with those cloud services, end user interfaces, stream analytics, SQL data warehouse, and then that little thing down in the bottom right, which is pretty interesting, called HPC. So this slide, then, there could be more things, say, from top to bottom on either side, but let's just say in general, this is an interesting way to look at a model. So if we skip forward a bit and consider MOSA and how MOSA is applied to the edge model, one of the things we noticed is how networks are being reshaped or how they need to be reshaped. For the DoD, legacy networks must be transformed. There's a need to transform the networks as they're used, actually probably on the commercial side and maybe on the mil-aero side, to continue to keep up with advances in technology. Along that line, Tri-Service are performing evaluations to see what actions should be taken and when this will occur. Another point would be in the mil-aero domain, the MOSA approach is essentially mandatory. If MOSA is not used, then how can the network, if one says, how can the network rapidly evolve? How can you plug in new technologies? How are you going to get there? Those are a few questions asked about it. So from a rapid absorption and adoption of technology, one's going to need to do that. But finally, on this slide, characteristics of the future network include, in broadly, resiliency, availability, multiple paths, quality of service, and determinism, or maybe TSN, as it's been mentioned a couple of times over the last couple of days. Excuse me. So looking at how the edge is evolving, there's a few points, and then my colleague Mark Littlefield's been making these points in some of his talks that are more pointed to the industrial sides of things. But one would be local high-performance computing for tight loop, low latency streaming. And when you might ask, what are we doing? Is that happening? And that seems to be happening now. And this could be addressing, or does, deep learning and the AI entering in that space. Another issue would be, or a potential that you need, might be link upstream to more heavy lift or specialized processing, where you might have bandwidth and latency limitations. You may have the need to reach up top to access compute resources or access AI services. And then the other thing you might be able to need to do is look at accessing models or information that you want to interface to the edge or you might need to take to the edge. And then three sort of examples below that: automotive, one of the huge spaces for autonomous vehicles across many vehicle types, needing to use this technology. Then in industrial applications, local object-oriented detection and recognition, and then quality of service, quality statistics being sent back up and down to the network to the other side. So if we look at technologies aligned with SOSA around this model, and considering the edge premise around the SOSA TS, there's a few points that might be relevant to take a look at today. SOSA can be used to implement edge compute and AI capabilities. And last year, we were able to participate in some of that stuff and do some demos. And at the SOSA F2F, I think in June or July, at NVIDIA, there were some interesting demos made that showed that we could actually start to do these things with OpenVPX construed platforms. So here, AI techniques can be implemented between two PICs. And that's basically the board. A compute-intensive SBC coupled to a GPU, or another way you might be able to do it is via SOM, system on module, and that may be able to contain in one PIC. What we hear from our customers as we have these conversations is that the AI component of these solutions, whether it's commercial or whether it's mil-aero, may be short-lived. In other words, the rate that things are happening, if you look at the horizon for the application of the thing you're going to build, it may only be useful for 3 years. It may be shorter than that, may be longer, but 3 years might be a good way to look at it. And this is when you can listen to the customer. So a couple other points: smaller form factors, what are coming there, swap C of it, and that area of interest. One might want to look at VNA 90 or VNX Plus as it emerges. So at the top, SOSA community, what's going on? A lot of that's been discussed already, fortunately, so we can skip over this. Maybe embracing new missions and modalities, like DEWs, or directed energy weapons, leveraging the strengths of what, let's say, MOSA, SOSA, CMOS, host, all that's been able to accomplish so far. And then if you look at the next point, integration and centralization of other standards. What's occurred in recent times, in the last 2 years, is Victory and Mora have become front and center and are being addressed within the SOSA umbrella, let me put it that way. And what's happening is this SOSA way is allowing those specifications to be maintained and be supported. And this brings me to another point that's kind of really nifty, I think. Applied middleware emerging around MOSA and OpenVPX that accelerate this development. 2 points here, and we've been able to show some of this in the last year, are more ready development platforms with frameworks that are pre-installed that help you with a leg up applying that middleware to start doing your real work. The second one would be SOSA-aligned platforms that enable rapid reuse and migration of existing AI, let's say, technology. And here I'm speaking more from a software point of view. So that brings me to this little squiggly line between all this and some recent observations that have taken place at the end of the year. So quantum emergence observed, being that Elma and myself, right at the moment, are observing some pretty cool things. So when we consider those, in 2020, when the year closed out, we had IBM's Quantum Summit, breaking some new ground, ushering in what they call the era of quantum utility, meaning useful calculations can be performed by a quantum, in this case, supercomputer, for very short bursts of time. And I don't have any idea what that short burst really is, but it's there, and IBM's pretty darn sure it's useful. So the next point is, you may have heard of a gentleman named Curtis Preem. He was the third co-founder of NVIDIA. He has had a foundation for years, and he's been making, or his trust has been making gifts to advance technology in different ways. Oops. So one of these things that just happened about 3 or 4 days around the Quantum Summit is that RPI becomes the first university to receive an IBM Quantum System 1, which is a supercomputer. And it's being installed. It may already be installed at RPI. So this is a busy slide. I'm not going to read everything, but when you look at what the significance is of what IBM's communicating to the world at the Quantum Summit, they lay out two or three really interesting points. One is they're establishing a 10-year roadmap, deliberate roadmap, with 2 parts to that roadmap for the next quantum devices that are going to be introduced year on year on year on year. So that's one. And then what they really did there is they laid out a bold technical path to produce a practical quantum circuit, meaning one that actually can be used outside of the research lab. And that has some requirements associated with it to bring it to market that are a little hard to dissect, but if one goes and listens to the 4 or 5 hours of content that's posted by IBM on the Quantum Summit, there's a lot to be learned. So one of those main things is a set of chips that now have reached 133 qubits, or a quantum bit. And in this case, there's one that's got a tunable coupler embedded in it, and it's called Heron. The long and the short of it is if you look at what's inside the IBM Quantum System 2, it's got 3 of those chips integrated into its processor unit. So this is the roadmap, and I'm showing it because IBM put it up. It's out there. It's very interesting. It works the problem from the top to the bottom and the bottom to the top. But the really interesting thing that they made a statement about is that they're pretty darn sure that within one standard business cycle, they believe that there'll be a practical emerged quantum computing capability. And it will actually be a hybrid quantum computing capability that's a supercomputer that links the classical computational environment to the quantum computational environment. So that picture at the bottom, that is System 2. And a couple other points. IBM's established online access for this machine. You can pay $1.60 a second, make an account, and actually start accessing a computer that processes hybrid workflows. So this is pretty significant when you start thinking about IBM being bold enough to lay out that roadmap, and at the same time, be fairly sure that they're going to make some real progress to getting the world towards a reliable quantum solution. And then this would be the latest offering, would be the IBM Quantum System 2. And to the right of that is actually the quantum processing unit with the business end of that at the bottom in the silver part. So what's next? In quantum emergence observed, this is sort of the third thing that happened towards the end of the year, which was like really cool. If you go on to 60 Minutes, and that link will take you to it, you can watch a news program that was produced by 60 Minutes with Scott Pelley that describes what this is all about. I contend it may be shocking. When you look at it, I had to watch it like 2 or 3 times just to begin to understand what the heck they were talking about at all. It's pretty darn amazing. So my recommendation, if you would like to, is go take a look, see what you think, maybe learn a little bit, and then we got on with our lives. Below that, we've got some pictures from Intel. So IBM, of course, not the only one doing it. If you look at the top 10 list of quantum computer developers, leaders, the top 5 are pretty much all the usual suspects, but IBM's in the lead. And then you have the top 5, and then the next 5. And a lot of those companies are all in the US, but this is a worldwide effort in research relative to this and leading up to it. So here we see a different view of another quantum processor from a company called D-Wave. And the point that this has got to operate at minus 273 C, and from what I've understood listening to this stuff, is this is actually colder than space. This has got to be completely, let's say, at a temperature that causes no noise to be induced into the quantum circuit. Here's another picture, different look from NVIDIA. This is right after the turn of the year off of their blog site. NVIDIA DDGX coupled to a quantum computing element with the dilution fridge on the right. And the thing in the middle is NVIDIA's way of implementing a hybrid workflow or coupling classic to quantum. So why it's compelling? Why are we talking about it? What's interesting is if you look at Moore's law standard, and then Moore's law of Moore's law, which is now called Rose's law, you can make a comparison between what's the difference between a classical computing environment and what is going to be the scalability and the behavior of a quantum environment. If you look at the chart here, as you go over time, you go from 3 qubits to 10 to 20, you see the equivalent classic view of that as 8 bits, 10, 24, and 1,000,000. But look at that interesting thing with the ... there. When you get to 300 qubits, which we're effectively at, the number of classical bits in the machine is that horrendously large number of 2 something e to the 90. Well, what the heck does that mean? So if you juxtapose Moore's law against Rose's law, and you make a couple of observations, one of those would be that on the right side, which is the Rose's law look of quantum growth, and on the left side is the traditional Moore's law look at classical implemented circuits, that it only takes 1 qubit to double the power of the quantum computing element. So a good rule of thumb when comparing the power of classic and quantum computers is this. Bits equals, that's actually supposed to be a power up 2 to the qubit, and so it got crunched down. But this is a way to translate back and forth between classic bits and quantum bits. So in summary, the edge to network to cloud computing is accelerating very rapidly. Networks are being transformed utilizing faster switches, better routing, and emerging AI. Multi-path network implementation between terrestrial devices and the cloud are being improved by layer interconnect that will continue to enable the future of the client server as we know it. Current enabled, AI-enabled hardware and networks and cloud services will continue to accelerate with AI devices like we saw at NVIDIA when we were there as SOSA with NVIDIA's Grayson Hopper that'll implement and do now enormous capabilities. And finally, with quantum computing coupled to existing AI, we are introduced to a whole new realm of capability. And this is seeming to be on the horizon. So what we've done is put a couple links into the presentation that help with the analysis of Moore's Law and the analysis of Rose's Law to give you some pointers and things to look at. And then there's also that link to the 60 Minutes piece that's fairly informative. So here are the links, the relentless pursuit of Moore's Law, and then Moore's Law, talking about how that really scales. And I think that's it. So I ask you if there's any questions.